Like it still appears in shit, no matter how you put it. Like you could be dumb. You could be like, okay, instead of drawing that, I'm gonna draw like a crazy line that squiggles all over the map, and then it's like, oh, it's right over here. Like, as long as it's connected to that node, it should.
I guess my question is, if you are drawing specific of three things like that versus like this, is it going to represent differently? No. So like this, how is this not simulated on the keyboard?
I mean, I love the game. Yeah. I don't imagine it's partaking in order. How did we do it once? So like I did for 3, the first 2 were fine. The last 2, when I tried to go yeah, I don't know, it just said
Oh no, you can just choose like stuff. Yeah, there's a transition like this. Yeah, you choose like a component that's like M-line stuff. Just like on there and then program this up. Oh, versus the stuff. It should not be, it should be and then you can choose like short circuit stuff, circuit stuff. Sure. And then the inductor is obviously. Like, it's a little harder with ADS not in front of me.
Right.
I don't remember there's like a stuff.
yeah. Shouldn't be that bad.
Yeah.
There was no like
Maybe you're not.
But,
like that.
I did.
Well, yeah, but then you guys make a combination of binomial, like the distribution.
Whoa.
No, after you have that, you gotta run X through, right? Double value of X. Then you use the binomial distribution to calculate that. And I was gonna print my homework out just to the machine to print out the quantity X, so I mailed out and I came in and said. Right now, it's like so you're gonna ask
I'm almost like one head. Do like the double column. Or just like like logic. Like actually do science. Sorry, man. I could do it up to them so impossible. Like, it's not little just like think of ways I provide like MATLAB code.
It's green and blue. Orange and yellow. It's orange and yellow.
If you look at the real dress.
What's strange is that at least half the class.
I didn't even know about it. They were talking about it in my stats class. Like everybody was talking about it in stats.
The internet
Dress,
is flipping.
yeah. about this brown or orange and blue dress?
I think I'm part of the minority here. I strongly see white and gold.
I can see it a little bit.
70% people see what I see. But my girlfriend and I just had an argument over this. And what's funny is then I read an article which basically is in Wired magazine, which tries to explain what's going on. But the author clearly had an argument with somebody because he ends it by saying, and people who see white and gold are utterly and completely wrong. So, but people who study optical illusions. So all of you have seen, for instance, the moving snakes. Have you seen that one? So anyways, there's a whole... Should I pull it up? Anyways, so it's what I read. There's an article in Wired magazine that tries to explain what's going on here. It's not... The interesting part of this, I think, is the social phenomenon, that everybody is talking about it. It's gone viral in such a profound way. But what's going on in the image, as far as I can understand, is our optical systems are very sophisticated. So those of you who take photography, you know that there's the issue of exposure. That exposure is how much light you allow to saturate what you're seeing. Now, our optical systems are such that if we're indoors, we see things of a certain color, and we walk outdoors and we can see things of the same color, even though what's hitting our retina, these are two very different images with the amount of light. So that's what's going on here. But what's fascinating about this is there isn't that much in the image. And even if you zoom in, so I tried with my girlfriend zooming into just a patch right here, with nothing else around, and I would still see white and gold, and she would still see black and blue. And so it's not here the question that it's the context that's the feature. It's really the feature of the exact exposure. Anyways. But this is what the dress actually looks like, this one. That's the dress. So pretty fascinating. So for those of you who saw black and blue, this doesn't look surprising. To me, it's utterly striking that it's the same dress. And also, the image above, if I just blew it up, I tried basically creating a blank background on the screen and then scrolling it up and down, like in and out of view. And that was really striking too, because what happened for me is, as it scrolled into view, it would initially appear dark, and then it looked like it was a dynamic image, that somebody was turning on the lights. And I could get this reproducibly to happen every single time I looked at the image. Okay. This was always one of my very favorites, for those of you who haven't seen it. I wonder if this will work. On a big screen, because you have to be a certain distance away. So I look at this and things are moving, like I'm tripping on acid. They're moving. I can't get them to stop moving. But in fact, I have a printout of this poster size. There's nothing moving. This is a static image. It's one of the best.
I heard it represents your ability to be able to handle stress. So like if you close your eyes and like then look at it,
Uh-huh.
it like moves slower for some people because it's supposed to represent how you're like.
So if you're relaxed, you're saying that they'll move more slowly?
Yeah, that's what somebody told me.
Interesting. Obviously, it depends where you focus. So if I move different areas, it's always the part that I'm not staring at that's moving. Okay, so what I'm going to launch into today, I hesitated a bit because logically, based upon what we've discussed so far, I should begin with something very simple. And it's not to say that I won't begin this talk with simple constructs. But logically, perhaps what comes next in the sequence of ideas is how we can synthesize chemistry to perform computation. So we've discussed analysis. We've discussed how if you sit down and write a set of reactions, you can analyze, interpret, describe what's going on. And I guess the example where we were looking at structuring a particular set of reactions to synthesize probabilities, that was synthesis. We were creating, designing, writing down a set of chemical reactions for a specific purpose, which was to compute probabilities as a function of quantities. But now what I'll begin for the next couple of lectures is showing you constructs that are very computer engineering in flavor. So this will be a talk that pertains to designing filtering operations or performing signal processing with chemical reactions. But these are chemical reactions, and in essence, chemical reactions have become our components that we work with. So the analogy might be if you're a circuit designer working with transistors, if you're a logic designer working with logic gates, or perhaps a good analogy might be if you're a programmer writing lines of code to achieve something. Here we're going to be doing any one of those tasks, designing circuits or writing code, but doing so with chemical reactions. So the operation that we'll target, and I decided to go with this one first because this particular line of research on filtering operations, this is a construct that works and is robust and illustrates topics like oscillation. Afterwards, starting next lecture, what I'll return to are more primitive operations, like just simple arithmetic operations, performing multiplication, and then moving towards programming-like constructs, if statements, while statements, for statements. But truthfully, some of those ideas on iterative computation, they don't quite work as well as they should, for reasons that I think I discussed when I presented one of those examples that I'll return to. But this example of filtering, we do this entirely at the DNA level, and it's really robust. It actually works in the sense that we can perform a moving average filter, or we can perform low-pass filtering with DNA reactions. Okay. But first, let's make sure we're all on the same page. So, for some reason, I have troubles talking today. Can someone who's taken a course on DSP tell us what is digital signal processing? John? Are you an ECE major?
Yes,
Yeah.
I am.
There's no tricky answer here.
I know, but I guess it's analyzing digital signals.
Yeah.
I haven't taken DSP, just
Okay.
the regular signal systems course. But
Yeah. Anyone else?
Trying to digitize digital analog signals and then analyze them so that it's faster?
Mm-hmm. So in terms of the jargon of the field, I should have unit markers. There is digital. And if you took the course on signals and systems, some people get very excited about the distinction between digital and discrete time signal processing. So discrete time signal processing would be where you're operating on analog values perhaps being real values. So I've had this issue before. As a student, I was standing in front of a poster, and I was trying to describe what my research was about. It was my first research in molecular computing, and people were milling about. It was a relatively important person who was standing in front of my poster, and I was giving my explanation. I was all pleased with the way I was explaining it. And I kept saying, and here, instead of integers, we're processing real values. This person happened to be a professor at Harvard. And then after a short discussion, the person said, so by real values, you mean experimental values that you've obtained versus theoretical values? And then I realized that there was a huge disconnect. So when I say real values, what I mean are values that are perhaps, you could describe them as values that consist of a fractional part and an integer part, fractional part, or they consist of numbers with numbers that have digits after the decimal point. Anyways, so discrete time signal processing would be signal processing in which you have values. Those values could be real values, but you have a discrete sequence of them. So I might have 10.2, 6.78, 10.62, 3.23, 25, so forth. But I have different values that come at discrete times. That's to distinguish it from analog signal processing, where what you have is perhaps just analog values, and the analog values arriving at every instant in time. Digital signal processing is where you have not only discrete time signals coming in, but those values are actual integers, 6, 11, 12, 1,000. Or in the language of computer engineering, those integers then would be binary numbers. Okay, none of this was interesting. But here, what we're going to attempt to do is create a set of chemical reactions that operates on a sequence of values coming in that will probably be more, this will be more like discrete time signal processing in the sense that what we have coming in and going out will be concentrations. But we have integers coming in and integers coming out. So what do I mean by integers in, integers out here? So John, help me out here. So what are the integers here?
I honestly have no idea.
Okay, that means I'm explaining it as bad as I think I'm explaining it. All right. So we're going to have a set of chemical reactions that describes the chemistry. That describes the set of rules that will operate on everything that we're working with. What I'm trying to indicate here is we have time-varying concentrations, which, or stated differently, you have a lab tech, you've got a test tube. The test tube describes the chemistry that will occur. And you've got a lab tech who walks over and every minute dumps a certain quantity or a certain concentration of type green into your test tube. So at 1 o'clock, he walks over and he dumps a quantity of 10. Then he walks over and he drops a quantity of 2, then 12. Then 8, then 4, so forth. So at specific time intervals, we have a specific quantity of the input type that's dumped into the system. Then we have a set of chemical reactions that operate, that fire on the types. In addition to the types that we put in, there may be types already in the test tube. And then what will come out will be concentrations of a different type, red, and we will measure those at discrete times. So at discrete times, we'll go and we'll look and say, what's the concentration? Come back in an hour. What's the concentration? What's the concentration? So this is the paradigm for the type of computation that we'll be doing here. In a sense, this is leaping right into a fairly sophisticated kind of computation because what we have here is sequential computation. We're operating over a sequence of values. It's not just a one-shot operation where we dump in a quantity 10 and then we get out a quantity 100. Instead, we dump in quantities, quantities, quantities. We get quantities. Okay. So time-varying changes in the concentration of different types. So here, what I'll show is first the circuit representation of what's going on. And this is perhaps poorly chosen because it's a fairly complicated circuit. But has anybody seen the circuit? Can anyone say what it does? Subhadnath, what does this look like? A filter? What kind of filter? I don't know the specifics, but why is it a filter? Just talk to us a little bit what's going on.
It's a FIR filter, I guess. And the delay elements where the input samples are shifted by 2 units. And each of the shifted inputs will be weighted by those constants and sampled together to form the output.
Perfect. The only part is I think this is actually an IR filter because there's the feedback path here. But otherwise, so I'm showing this here not to explain what's going on in the circuit, but to introduce you to some of the circuit constructs you'll see. Starting next slide, I'll begin explaining things in a measured way and explaining them properly. But the point is here, the circuit representation of the function that we want to do. On the previous slide, I showed you the goal. The goal is to take a sequence of values in and produce a sequence of values out. In the electrical engineering world, this is a circuit representation of a particular function that fits that mold, and this is a filtering operation. So to describe what's going on, the input comes in along a wire. Then the input is summed together with some other value. So a wire, an arrow going in to a bubble that has a plus sign means a summation. That's pretty straightforward. If I have 10 coming in and I have 3 on the arrow, then the output is 13. So that comes out. That flows along here. If I have a given wire that splits, that's called fan out. That's as intuitive as it sounds, but it actually means duplicating the value. So if I have a wire that splits, I have 10. I now have 10 traveling along there, 10 traveling along here. If I have a box like this with an X, this is a multiplier. That's as intuitive as it sounds. If I have 10 coming in and I have 3 coming in, then I have 30 coming out. So I just have the values that flow through my circuit that way. The only other element that I haven't explained here is the box that has a D in it. That's called a delay element. This is what makes this entire circuit interesting. What the delay element does is it holds on to its value for a specified amount of time. And so the delay element can hold it, let's say, for 1 second. What this means is, as the values flow through, when they hit the delay element, they're delayed. Nothing happens to the output of the delay element for 1 second. And then all the delay elements, even if values arrive at slightly different times, produce their output values at the same time. So they kind of synchronize on the next 1 second boundary, let's say. So they hold on to their values, and the values come out. And then they flow through additions and multiplications, and the answer comes out. Okay. So this particular circuit does a function, but the point of showing it to you is just imagine we had the green box on the previous slide, and the purpose of the green box was to take values in and produce values out. This is a topology that would do that. Values flow in, and based upon the values that were already in the circuit held by the delay elements, we have values flowing back, multiplies, and we have additions, then we have values flowing out, and the machine will continue running like that. So that's just a generic circuit representation. Now, let's talk a little bit about this. Suppose that instead of electrical signals or digital signals flowing in and out, suppose that we have molecular values, concentrations. The circuit analogy or the circuit diagram is still helpful because I think, I'm biased of course because I have the background, but I think it's a good way of describing the operations. But it's misleading in the molecular context because we don't have wires that route molecules around. So this is not an exercise in routing molecules around. Rather, we'll have reactions that are rules that operate on certain types. And how we structure those rules on the given types to perform the operations will not be so obvious. But let's start with a couple of the simple operations just viewed in isolation. So suppose that we want to multiply a concentration by a constant value. The constant value being some number, let's say B over A. How can we do that? So Ryan, how can we do that? Yes, yeah.
How about just put it in a reaction which coefficients is P and A?
Yeah, very good. So I hope I show that here. Hang on. I thought that was on this slide. Okay, so write it down. If I want to multiply an input quantity x to have an output, let's say, that's going to be y, and I want y to be equal to 2x, then what should the reaction be? X goes to be 2y. So if I have this reaction and I put in an input concentration, or let's say an input quantity of 10, and it fires to completion, then I will have twice as much y that I had, twice as much y as the output as I had x at the input. So this is a constant multiplier, simply a reaction in which we set the coefficients to be the value that we wish to multiply by. And we could also have a fractional value. Let's say if I put in 3x goes to 2y, then what would I be multiplying by? Yeah. Two-thirds. Am I getting this wrong? Sometimes I do. Hang on. I think that's right. So if I just set up reactions with coefficients 3x goes to 2y, or if I set up reactions with, here's what I usually get wrong. So this is a b over a multiplier. And the b should be the coefficient of the output. The a should be the coefficient of the input. Okay, so that's very straightforward. If I want a reaction that multiplies an input quantity by a constant, I simply choose a reaction with the coefficients corresponding to the multiplication operation. Chopin, is this okay? You look frustrated.
I'm not sure how you're getting the y from the x though. I mean, the amounts are okay, but like there should be something that's actually changing the x to y.
Well, the thing that's changing x to y, like, I mean, suppose that I had H2 plus O going to H2O. It's a reaction that's changing input concentration. This is not how it's even written. But I have input concentrations of H and O, and I get H2O. So here I have a reaction where I have X as the input and Y as the output. So what is...
Like if you put nothing else, then I mean, X is supposed to remain X.
No. So you're... that's... somehow if I write a reaction like A plus B goes to C, everybody's okay with that.
Yeah.
But if I write a reaction X goes to Y, this is why on the previous slide I put in the mysterious N when I was doing the exiting from the probabilities. This doesn't look like a reaction anymore. But, you'll see when I discuss DNA-based reactions, we can choose any reaction that we want to implement. How is this implemented at the lower level? Well, at the lower level, you're going to have something like a fuel source and a waste product. So what happens is there is some fuel source that you put into your system in abundance, and then you put in the amount of X that you're interested in. The amount of X reacts with the fuel source to produce the output and produce some waste type. So this means that in a lot of the reactions that I write down, a chemist or a biologist immediately objects that the reactions appear to violate the conservation of mass and so forth. And that's simply because at this higher level, I'm not including the food and the waste sources. But if I do include those, then it's a proper chemical reaction. Is this your concern?
Yeah, that's one part of it. But now since I put them in, isn't the F going to affect how much Y is produced? Or is it just dependent on the X?
Well, suppose that you have a large quantity of food. Suppose that, what's a good analogy? What kind of creature eats food voraciously? I guess many creatures do. But so you've got... Louis C.K. has a great little bit about, because he's a comedian who's, in essence, a manic depressive, like in his tone often, but he can be surprisingly optimistic. So he says, as people, we complain about a lot of things, but our lives are pretty great. Every other animal out there lives its life until the point where somebody eats it, and that's how it dies. So we have the luxury of not dying in the jaws of some other creature. And it's true that out there You live and perhaps you eat creatures, but most of the time, your life ends when you're eaten. All right, so you've got some food source. That's some abundant food source, a lot of it. If this was the only reaction operating on X, there was nothing else that X interacted with, then you dump in your quantity of X, and X would react with F, basically until all the X was gone, and until you had as much Y as you had X previously. Of course, as the quantities of X get very, very small, the rate of the reaction is going to drop, but to an approximation, the quantity of Y that you're going to get will be the amount of X. Yeah. Okay. So that's all I'm saying here. The constant multiply operation, and you're hinting at the subtleties that are to come in this discussion, because here, a given reaction in isolation seems to work. It seems to perform our task. But we're going to be combining these reactions. And then it's not so obvious. If something else is operating on X, then our scalar multiplier or our constant multiplier won't work. Okay. So now how can we do addition? We wanted to do multiplication by scalar. How can we do addition? Any ideas? Yes, Ron.
B goes to C.
Well, what we want here is we want some input quantity of X, some input quantity of Y, and we want the output quantity to be Z, where the quantity of Z should be the sum of A and the B, X and Y. Sorry, I'm tired today. I'm messing everything up. So your suggestion was A plus B goes to C?
Or 2C.
2C? But the problem with that is that if A and B are not equal, we're going to run out of one or the other first. And it turns out that as much C you're going to the quantity of C that you're going to have is going to be equal to the smaller of the two quantities times 2. So that's not quite what we want. Do you guys see why that doesn't work in itself? Any other suggestions? Yes?
You just have two reactions. A goes to C and
Perfect.
Y goes to C.
So it is that simple in this context. If we want, we just have two reactions. One reaction so the quantity of X goes to Z. You dump in, again, there can be some food source and some waste. Let's call this Fx. So some food source plus X takes the full quantity of X, combines with the food, makes a bunch of Z. Some food source for Y takes the full quantity of Y plus the food source makes Z. The total quantity of Z that I get after all the X and Y are gone is going to be equal to the quantity of X plus the quantity of Y. So it's that simple. And it turns out the addition, or the addition blocks in the circuit diagram, they're very easy to implement because I don't have to do anything. If I just have two separate paths, I just have to have both paths produce the same output type. It's like in circuit jargon, this is like a hardwired OR, or it's when you connect two wires together. In some circuit design paradigms, you simply get the summation, for instance, of the current. The total current flowing out will be the sum of the two wires. All right. Now, the delay element in the circuit is the... Yes, Chopin.
How do you implement the multiplication then? I mean, like in this case, you can actually have two parallel reactions. How do you set the coefficient for the B by A? I mean,
so for B by A, so if we wanted to multiply, if we want the quantity of the output Y to be B over A times the quantity of the input X, we'll just set up a reaction that is AX goes to BY.
I mean, you actually have to find some reaction that actually matches this criteria.
Well, so that's the persistent criticism that you can offer in everything that I'm discussing, but one in which a criticism for which there is actually an answer. Everything is going to be in terms of those DNA reactions, DNA strand displacement reactions. And with the DNA strand displacement reactions, it's this very specific paradigm where I'm going to call X the concentration of a strand of a particular type. The type will be a particular sequence of ACTs and Gs. And I'll call Y the concentration of another type. a particular strand of ACTs and Gs. They will react in very specific ways. And they'll react in ways such that I can choose any reaction I wanted. Like I can choose a reaction 2x goes to 3y. And I can implement this reaction with those DNA-based reactions. So suspend your disbelief on where x comes from, where y comes from, what kind of chemistry will give me this reaction, until a discussion where I present to you the DNA-based reactions that can implement all of it. But for now, just accept it more or less like a computer scientist would. This is simply the fundamental operation that we're working with. It's kind of like a logic gate or a transistor gate. We have a reaction. We get to write down whatever reaction we want, and our goal is to build something useful out of that. Okay, so the constant multiplier and the addition, these are very easy. The delay operation is what I'll spend a whole sequence of slides implementing. And as it turns out, to do digital signal processing with chemical reactions, everything revolves around the delay operation. It revolves around the delay operation because what we have to do here is we have to synchronize the computation. We have reactions firing, producing stuff. But the whole reason why we can do filtering or digital signal processing is because we synchronize what happens. And the synchronization happens at those delay units. If we didn't have those delay units synchronizing it in an electrical circuit, we would just have voltages and currents racing around and we'd have chaos. So there too, it's at the key. So any ideas? How can we implement a delay operation? Yeah.
Is this just a delatch?
It could be like a delatch, but
So if I can see it as a delatch, we can just implement a reaction like x goes to y as a rate which should be controlled. And I think the rate should be very, very slow to give other reactions.
That's a good suggestion. So you're saying that to implement a delay reaction, a delay unit, let's just start with an extremely slow reaction. So everything kind of comes to a halt until an extremely slow reaction performs the delay.
Could you use some intermediate product, something,
And
have two rate constants of two reactions that are equal,
and
that's relative to some clock that you have, so it gets held in the middle.
Yeah. But part of the problem with this is even if the delay operation is incredibly slow, if we have so if we have A goes to B, so in our box what we have is a bunch of computation producing a certain quantity of A. Then and then B comes out, this might go to a bunch of computation. We want this to be a delay. So here, we just make this reaction extremely slow, maybe 1,000 times slower than everything else. But that doesn't quite work, because here we have the quantity of 10 coming in, or the concentration 10. But then this reaction takes molecules of A and makes molecules of B. But it does so progressively. So initially B is 0. A is 10, B is 0. And then after some amount of time, we get 9, and we get 1. And then we get 8, and we get 2. And this is happening slowly. But it means for the rest of the circuit now, what's it seeing? Well, it's seeing a value of B equals 2. And so the rest of the computation will start happening. So does this give you a sense of what's going on? In an electric circuit, it's more complicated than that. You can't just, so to create a delatch, you don't just put a delay element. You do much more, right? So what is a delatch built out of logic gates?
Built on the clock.
There's a clock, and everything happens on the synchronization of a clock boundary. So you don't simply allow an analog value or even a digital value of 10 to trickle through and slowly build up. Because the problem is then the rest of the circuit already begins computing on the values it's built up progressively. It begins doing stuff. And you have no guarantee that that stuff won't feed back around. Yeah. So Ron?
I guess the way that you describe the circuit, what it reminds me of is like
the addition and the multiplier are like continuous processes.
Yeah.
And then the delay element would be like a batch process.
Yeah, that's a great way to describe it here. So, as you describe multiplication and addition, we do those progressively. We just have the reactions consume the input type, produce the output type in the right quantity. And in our circuit diagram, we allow that to happen throughout for a multiplication and addition. But the delay elements are, what was the word you used? They're latches?
Batch.
Batch?
Batch reactor is when you just sort of just toss some stuff and wait a certain time.
Yeah, so adders and multipliers are. But what was the word you used for the delay element?
No, as in like for adders and multipliers,
Yeah.
they seem like continuous
Yeah.
processes where you continually just
Yeah.
add elements and
Yeah.
the output is continuous.
Right.
But in a delay element, it seems like a batch process, like
Mm.
with a B.
With a
where
B.
you sort of throw stuff in a reactor, wait a certain time, and open it up. And
Yeah, that's a good way to say it. But that means that there is a person who's actually holding a gate that they wait, and then they pull open the gate. But but any ideas? So how can we do that here?
We could use a like third of the element, like one of the. So as you showed, the A goes to B. That's with the help of a like food product. So unless the F doesn't exist, it won't go.
Sure.
So we can hold back that, like
Yeah.
I want it to progress only, then we add the F.
Sure. But we're not going to rely upon a lab tech or a person to walk over and put the food. So,
F can be produced by a third set of reactions that's triggered by something.
but that third set of reactions won't produce your quantity of F instantaneously.
Yeah,
The F will start to trickle in. And as the F starts to trickle in, the reaction will start to happen and the output will start to trigger out.
We can have a reaction with a very high rate constant, so that it'll.
Yeah. So those are all very good ideas. But I hope you can all appreciate the subtlety here that we do have to build a delay element that somehow behaves like a dam. Imagine there's a river flowing, and it holds all the water until we open the dam, and then it all flows out very quickly. Having some sort of reaction that very quickly produces the opening of the dam is a good idea. I'm going to present a different idea, which is actually quite sophisticated. I'll show you. It's based upon two-way handshaking. So the metaphor is the output. We produce none of the output until a signal tells us we're ready to accept the output, and then we begin producing the input that produces the output. So just bear with me, but you'll see that it's that sort of flavor. That's one variation. But then, probably in the next lecture, what I'll show you is a method where we actually use an explicit clock. So we use oscillation. We use chemical reactions that produce a type going up and going down. And everything only happens when molecular types are going up. So it only happens on the rising edge of the clock. Okay, but let's proceed in steps. So that's going to be in the next talk where I'll show you how to build the clock and synchronize it. But what I'll describe here is instead an asynchronous methodology or a methodology that's self-timed. But the critical point is that what I'll describe, I don't want the results of the computation to depend upon the rates. So that sounds like a statement that, like the white and gold dress, that you either accept or vehemently protest. Because, in essence, all chemical reactions depend upon the rates. But what I want is I want the circuit to produce numerical values, which will be the numerical values of my operation, the correct numerical values, independent of the rates of the reactions. And this will be a theme for all the constructs that I show and the research contribution, because other people have talked about chemical reactions computing. But in the schemes that other people propose for this, you have a system that, let's say, does multiplication or does some more complicated function. But it does so for particular rates. Now, the rates, which are the parameters k of the reactions, these are referred to as rate constants, but as we discussed last time, they're not really constant at all. They're dependent upon things like temperature. So Jesse, the value k in a reaction, what goes into the value k physically?
It will go into the radius of a
a sort of hard sphere
Yeah.
model of each
Yeah.
molecule involved.
But you increase the temperature, you increase all the K values, right?
Right.
Yeah.
And temperature,
Uh-huh.
as you said. The average molecular speed, which again is related to the temperature, and I believe the activation energy for the reaction.
Yeah. So there's a lot of chemistry that goes into the rates, but the basic point is that chemistry, if you heat it up, molecules bounce around faster. And to put it into stupid terms. But it means that if you structure a computation that computes a function, but the function, so let's say you design a black box. That has quantities in x, and here it has quantity y equals some function of x. But that function is something that will have, k1, k2 times log base 2 of the concentration divided by K1, K2. I'm just making up a formula here. But the computation other people have proposed to say, look, we have a circuit that computes the log function. But it computes the log function with the parameters K1, K2. So the actual function that it computes is very much dependent upon the temperature and other factors of the reactions you choose. We're going to strive for computation that computes the correct expected outputs independent of the values of the rates of the reactions. And that's more challenging to do here. So that's what I mean by rate independent. So now, finally, let's begin to talk about something concrete. I think I showed you this example, but this is going to be a basic part of many of the constructs we use. I'll call it the absence indicator mechanism, but you can also view it as inversion. So this is a sequence of 3 reactions. It kind of looks ugly, unfortunately, because I've got the AB subscript here. That stands for absence. And unfortunately, on this slide, I chose A to be my type. So that kind of leads to the A subscript AB, which is ugly. And ignore this reaction for the moment, but just look at these 2 reactions. So, Ryan, what's going on here? What do these 2 reactions do? And why am I claiming that it inverts a quantity? And by invert, we start by saying, suppose we have a lot of a quantity, then this will invert that value. And we'll have very little. Or if we have very little, we have a lot. So think of it as a seesaw. So the quantity that we're going to invert is going to be the quantity A. Okay, yeah, quickly.
Sometimes you want to assign the value of AB to A.
Yeah.
And I still don't know what's the AB for.
What's the AB for? Okay, so let me describe. So what's going on here? Somehow, and this is a well-rehearsed sequence of slides, but today the presentation is not going as well as I would like. Let me try to do better. So here, suppose that we have some concentration of A going in. Then what we're interested in at the output is going to be AB. So that's the input-output representation. The way this works is, as part of my system, I'm going to have some source that continuously produces AAB. Think of it as a gun, a sputter gun, that's constantly spitting out AAB, just always. So it means that AAB naturally will tend to accumulate. So over time, I'll have a lot of AAB. But suppose then I dump some quantity of A into the system. Well, then I've got this fast reaction that kicks in. Quickly, all of the A that I dump in will react with the AB that's present, just giving me A. And so it'll quickly clobber the full quantity of AAB. So if I dump in a significant quantity of A, then what do I get at the output? Well, I get very little AAB. So I get the inverse. I had a lot of A, I've got very little AAB. But conversely, if I don't dump any into the system, or I dump very little into the system, then I will have AAB. So it's that simple. Is it making sense? It's an inverter. It gives me the opposite of what I had before in terms of a lot or a little. Now, what is this reaction doing? This reaction is just throttling the growth of AAB so that AAB will continue to grow, but we won't let it grow out of control, because if we let it grow out of control, there is some food source that is producing AAB. Okay, but this mechanism is going to be ubiquitous in much of the presentation, meaning I'll often just refer to some type X, and then later on I'll refer to some type X with subscript AB. X with subscript AB is a different molecular type, but it's going to be a type that will have a high concentration when X has low concentration and vice versa. And implicit whenever I just throw in quantity XAB is I've got these three reactions lurking in the background that actually produce XAB, the absence indicator mechanism. Okay. So now here is perhaps the first interesting construct that I'm showing you. This is a construct that duplicates a given quantity. So the idea is that if I dump some quantity y into the system, what I want to come out will be, I want the value of y to remain unchanged, but then I want an output quantity of z, where z is equal to y. So I'm going to duplicate a quantity. Exactly. So how does this work? So, right? Now, there are some other types that I put in. So there's going to be an intermediate type y prime. That's just produced by a reaction. But there is going to be this molecule G, and that's going to be my go molecule. Because this is going to be a synchronized duplication. So I don't want the duplication to happen at any random time. I want the duplication reaction to happen when I dump some quantity of G into the system. And as you'll see as I build up constructs, this notion of the go molecule, and there's going to be go molecules for different blocks, is going to be key. And the go molecule may be produced by some other blocks. We'll have some other block that produces some type, G, that then causes the next molecule to go. Okay, so Ryan, how's it going? Anyone? Yes, Jacob.
The G turns Y to Y prime.
Yeah.
And then it keeps going until all the Y is gone. And then when the Y is gone, then the Y absence is going to be there.
Mm-hmm.
And then that'll get rid of all the G's slowly.
Perfect.
And then once all the G's are gone, then all the Y primes turn back into Y plus Z.
Perfect. I'll repeat that. But you got it exactly. So I hope some of the symbols aren't throwing people off. This null symbol, I sometimes use it as a reactant, sometimes I use it as a product. If I use it as a reactant, then it simply means there's some food source, or some food source that we don't track that's generated. If I use it as a product, this is just some waste source that we're not tracking. So the null symbol is simply we don't care. But it doesn't mean that there's no reaction. So what's going on here is initially I have some quantity of y that's in the system. Then I decide that it's time to go. So I walk over and I dump some quantity of G into the test tube. What happens? Well, this is the only reaction that can happen for the time being, so it fires. And fires producing as much G as I had Y. But it consumes nearly all the Y. So nearly all the Y is consumed. And the quantity of G remains unchanged. And this reaction proceeds. It proceeds basically until all the Y is gone. Why? Because the next reaction will only happen once YAB appears. YAB will only appear once nearly all the G is gone, once nearly all the Y is gone. It's the absence indicator for Y. So first reaction fires until all of the Y is transformed into Y prime. Once all of the Y is gone, then YAB pops up. What does it do? Well, it clobbers all of the G. So however much G I put into the system, the Y absence indicator consumes all of that until nearly all of the G is gone. Once nearly all of the G is gone, the G absence indicator pops up. When the G absence indicator pops up, we take my quantity of Y prime and convert it back into the original quantity of Y as well as into Z. So the conversion here happens one reaction at a time. So the reaction fires, it's a little discrete event, but these reactions fire over and over again until a full quantity of inputs goes to the quantity of outputs. Does this make sense to everybody? So this is a, yes, Shubham.
So what exactly are those absence indicators? Are those some types of molecules or?
Everything will be DNA strands here. So everything will be DNA molecules. And each type, so each letter that I ascribe to something, will be a specific DNA strand sequence.
So when you mean that Y abscess appears only when all the Y is consumed?
Yeah.
From where does it appear? How does it appear?
Oh, so it appears because implicitly, for each type for which I introduce the AB subscript, I've got these three reactions lurking in the background. So here, for the Y absence indicator, it means that I have these set of reactions that produce YAB. So replace A by Y on this slide. Make sense?
So E and AB, I mean the Y and YAB can actually be present together, but
Well, but this set of reactions will ensure that the YAB only appears and persists when I have very little Y. And conversely, if I have a lot of Y, then I don't have the YAB. It's just this back and forth mechanism. Yeah? This back and forth mechanisms, I'm constantly generating the absence indicator, but if I have any quantity of the molecule present, it gets eaten up quickly. Making sense? It's good that you're both critical and vocal of this, because when I present this, sometimes my impression is that people don't really buy it, but they don't really object either. So it's good if you don't buy what I'm saying to tell me that you object. Well, no, where are these things coming from? But implicit here, since I have GAB and YAB, I've got three reactions in the background generating the GAB. Three reactions in the background generating the YAB. And, yes, Jesse.
How are you making sure that your YAB and GAB aren't degrading down by like a half quantity because you have two like XAB going to, and that's very fast, whereas those reactions were slow?
So how am I ensuring that I have enough of the GAB and the YAB?
True duplication.
Yeah.
If you're, that's fast. Yeah.
That's fast. That's a good question. The reason is when we actually went to DNA-based reactions, there is some fuel source that's generating our absence indicator. And so if we don't throttle the growth of AAB, then we have a problem. Then each absence indicator grows to be a very large quantity, because there's nothing that consumes AAB in the absence of a type. And then, but it's a good question. I don't have an answer for it. Let's return to that when I show you the specific construct. Yeah, Seamus?
You could say that at some specific concentration, your generation of AAB is going to be at about the same rate as that last reaction that's being consumed.
But here I've listed it as slow versus fast. Yeah.
So you have to change that.
Yeah.
And then you become rate
dependent. I don't want it to be rate dependent. Let me return to that. Return to this issue once I show you a full system that does something.
Another question on this slide, the previous one. Yeah, so which reaction here limits the production of A, because I can only see like getting produced more and more quantity. So,
but here, nothing is generating A in this set of reactions. A is unchanged by this reaction. So A is going to be the signal that comes in, or in this case, Y or some other signal. So that's going to be the quantity that's generated outside of these three reactions.
So when you say AAB is produced only when A is not there, so AAB shows up only when A is not there. Mm-hmm. So in this reaction, AAB is not going to show up ever, because A is always there.
Well, but in a different scenario, in a different phase of the computation, I won't have A, because something else is going to consume A. So if something consumes A, something external, then suddenly A and B will pop up. That's all this is showing. And then if something later produces A, the quantity of AAB goes down. In terms of this third reaction here, let me get back to you on that. Okay. So now, again, things are going to get interesting or complicated quickly in terms of what I'm going to present. But the essential idea is to implement the delay operation. We're going to have what, in essence, is oscillation. But it's oscillation that's self-timed. And it's going to be self-timed oscillation. So what does that mean? It means that the system is going to predictably go through 3 phases. So it's going to go through an R phase, a G phase, and a blue phase, and then an R phase, a G phase, and a blue phase. It's always going to turn around like that. Think of it as a wheel. It can only turn in one direction. It goes through RGB, RGB, RGB. The wheel can only turn in one direction. It will always turn forward. But the rate at which the wheel turns will depend upon the input that we supply. So this entire system will be doing a signal processing operation, meaning there'll be some input quantity X that will dump into the system. That's the external event, and that's the only external event. So the external event is somebody walks up, takes some quantity of X, drops it into the test tube. The system then will perform a bunch of reactions and completely consume X. So all the X will be consumed. And consuming the X will turn the wheel all the way from R to G to B to R. And the system will then wait. It'll wait until somebody comes along, dumps some quantity of X in the system. It'll consume all the X and turn the wheel all the way around. So that's the metaphor of where we're going. And this will be how we affect a proper delay operation in terms of what's going on in the computation. Will all be timed. It'll be timed through oscillation, meaning something will go up and something will go down. The RGB quantities will go up and they'll go down. But they'll go up and they'll down and up and down once around the cycle, and then they'll halt. So that's how this will work. And the essential idea is that we're going to move between the 3 phases, between red, green, and blue, in the absence of types. So how can we move around, Jacob? How can we move around from red to green to blue using the absence indicator type? Yeah, it's true, you walked out. But you're quick on your feet. When I was in grad school, there was a guy, I got to know him well. He was a particular strange kind of genius that infuriated professors. So he would always walk in late. Sometimes the classes were small. And he would have his skateboard, and he'd make a lot of noise as he settled in the front row. And he typically sometimes unwrapped food, and so it would be very disruptive. But then, 30 seconds after settling in, halfway through a lecture, a complicated lecture, he would ask a question that was exactly spot on, perhaps pointing out a mistake in what the professor was saying. And it was a particular kind of genius, and I think he enjoyed it, that he could just walk in and, having missed the first half of something very complicated, immediately understand what was going on. Okay, so, but anyone else while I was babbling? So the essential idea here, and again, I'm just setting this up progressively, is we're going to go from a red to a green to a blue phase to a red to green to blue, red to green to blue. The way it's going to work is we're going to move from red to green in the absence of blue. So if we have no blue, in the absence, wait. Yeah. So in the absence of blue, we're going to move from red to green. And then we're going to do this until all the red is gone. Once all the red is gone, then we have no more red left. So in the absence of red, we're going to go from green to blue. Until all the green is gone, then in the absence of green, we're going to go from blue to red. Then once all the blue is gone, in the absence of blue, we're going to go from red to green. So that's the essential idea. And we need 3 types to do this, because it's always, in the absence of a third type, we move between 2 types. And moving between the types is a progressive operation. Or, so Ron, what did you call this? It's
continuous.
A continuous operation, which means that, let's say if we have some quantity of 10 here, we'll transfer it to 10 here. But it won't happen instantaneously. It's going to go 10, 0, and then it's going to go 9, 1. It's going to go 8, 2. It's going to be a progressive operation. But that operation is going to continue until it's done, because it's going to proceed in the absence of blue. Now, the reaction that begins taking green to blue will only proceed once all the red is gone. Yeah. What's your name? Akash.
But like in a system that has some upstream elements, basically, if you keep feeding red in, then at the say what's there to say that you'll never run out of red to stop?
Good question. Well, that's a very good question. But in essence, the red part is going to be the external quantity. And this is the paradigm becomes discrete time signal processing precisely because there is an external input that's injected at discrete times. But that's the only assumption. So everything else internally operates on its own. But I assume that externally someone comes along and dumps some quantity of red into the system. And then the system proceeds until all the red is gone. Now, if the user continually adds red, he doesn't stop, then he's going to mess up my system. Or if the user dumps more red the next input quantity before I've consumed all the red, then he's also going to mess up my system. But suppose that the whole rate of my chemistry is fast. It maybe takes a minute, and the user comes in once every hour. Then we can reliably assume that all the red is gone, the system is stalled, waiting until someone dumps the quantity in. But the point is, as you'll see, we can implement this crisp delay reaction through this three-phase delay mechanism. Yeah, go ahead.
Firstly, what makes it stop once it gets back to red again? Why wouldn't it just keep going around and around?
Right. Because what I haven't pointed out is there's also going to be the output, which is going to be colored blue. And the system will stall until some external source consumes all my output. So just bear with me. It's going to be timed both at the input and the output.
Yeah. And then my second question was, earlier when we were kind of making suggestions of how to do a delay.
Yeah.
And our suggestion was some sort of batch reactor or some sort. And you said, but then you'll have to have a tech aid being there every however long to open the gate.
Yeah.
Aren't we employing that exact same?
You'll see that we're not. The only tech aid that comes in is the person who consumes the output, and that's your product. And then some other tech aid who comes and supplies the input. Or we can have other reactions that supply input and output. But otherwise, internally, we will not have somebody affecting the batch operation. Just bear with me until I begin to present the reactions. But I hope, and then I'd appreciate comments. Yeah, questions?
I think this is, now we're talking about the three-phase game, but I think this is just a generalization of two-phase game, and the two-phase game is just inversion. Is that right?
Sort of, but if you tried just using the absence indicator, it wouldn't work, because here you can't have a reaction that takes the full quantity of red to the full quantity of green, and does so until it's done, and then begins taking green to red directly.
No. I mean, we take the blue molecule as a absence.
Yeah, correct. So, but in this case, we'll just call it blue absence. So we'll have the blue absence indicator. Let me begin to show you the reactions. But first, going so slowly today, the target operation that we're going to appear here is useful to understand at the outset. So the target operation that we're going to do is very simple. I began showing you a very complicated circuit. This is a very simple circuit. So quickly, Jacob, what does it do? I call it a moving average filter. Why does it work?
It averages the current value of the previous value.
Perfect.
And it filters out high frequencies because those vary a lot and they would tend to cancel out.
Yeah, perfect. So I think I showed you a description of this early on. Here, if we have some input that looks like this. So here I'm trying to simulate discrete points. Goes up and down. The moving average, what it does is, for the output at each point, it takes the current input value, and it takes the previous input value, and it averages them. So it averages a window, in this case the window is only 2 input types. You could have a larger window. Well, let's say you could take the last n values. You could average the last n values. This is a simplest type of filter, but it's a very useful one because what it does is it will smooth out your curve. It will smooth out your curve in the sense that if there is a high frequency component, high frequency jitter, the moving average, because it averages out the last 2 or last n values, will produce a smoother version of the curve. And the larger the window, well, you have to match your window size with your high frequency noise, but it can be very effective. So in the early days of audio processing, in audio processing you can often have high frequency noise, little pops on top of your signal, which is your voice. A simple filter like this can clean out the high frequency noise. And that's going to be our goal here. And I think it's an interesting application because it's simple enough to state and simple enough to describe, but potentially useful. Okay. But in terms of the circuit diagram, how do we achieve this, Jacob? So what's going on? We have the input coming in, the output coming out, and how do we achieve the moving average part?
The current input just gets cut in half and then added
Perfect.
right to the output, and then it's saved for later on the...
Perfect. Perfect. So we take the input, and the first operation is we do have to split it. And that's an operation that we have to implement. So we take the input value, we split it, or we duplicate it. Recall the duplicate construct. We take the 2 copies, we cut each copy in half. So that's going to be multiplied by a half, so the scalar multiply operation. Then we take 1 copy and we feed it into a delay element. So we hold on to it for 1 time unit. The output then is going to be 1/2 of the current value plus 1/2 of the previous value. That appears. This is a continuous process. The next input comes in, gets cut in half, and the current input gets summed with the previous one. So we get always 1/2 current plus 1/2 previous in a sliding fashion. It's a very, very simple circuit. Now, so the fan-out we know how to do. The multiplication and the addition I described how we can do. Everything is going to be in the delay element. And the delay element here will be implemented through this 3-phase mechanism. But it's going to be a 3-phase mechanism that proceeds based upon the input and the output. The input and the output, somebody supplying the input and taking away the output is going to be critical in terms of what goes on. Okay, so, but just to illustrate, quantities, they get cut in half, the output appears. This is just a graphical illustration. But to be clear, I hope it's clear to everybody at this point, we don't actually have channels that are routing fluids or quantities of molecules. The circuit description is in terms of what goes on. We have to affect that with reactions. But this just illustrates output quantities as a function of input quantities. Okay. So how is this going to happen? I'm getting closer to a set of chemical reactions. The delay element, this is just a graphical description, the RGB compartments. Because what we're going to be doing is taking a quantity of red, which we'll call the R quantity, transfer it to G, transfer it to blue. The RGB transferring process will affect our delay. It'll hold on to the value for exactly the right amount of time. How long? Well, the right amount of time here is determined by the amount of time that it takes you to remove all of your Y, and then you're ready for the next set of X. But how will this work? Well, I was given this advice a long time ago. You should basically never use light green in your slides, because light green on projectors is basically illegible. That's a light green for the G. So here we're going to have R going to G, capital R going to capital G. And here, to be inconsistent for simplicity, I'm using lowercase letters for the absence indicators. So previously what had an AB subscript here is just going to be the lowercase letter. So it means here that this lowercase b is the absence indicator for the capital B. It's a molecular type that's only there in the absence of capital B. But in the absence of capital B, and I'm starting right in the middle, but in the absence of capital B, we have the lowercase b, we have the reaction that will take my full quantity of R and transfer it to the full quantity of G. Then a reaction, so I have some quantity of R sitting at the input to my delay element, and since I have no B anywhere in the system, no capital B in the system, and in fact, sorry, I got the colors confused here. X here is going to be colored blue. So the lowercase b will appear in the absence of a capital B, but also in the absence of an X, because X is colored B. So anything colored B is blue, and in the presence of anything colored B, I will not get a lowercase b. But if I have the lowercase b, then the reaction R to G proceeds. Okay. Then my full quantity that was sitting at the input of the delay element has been transferred to G. And then we have a reaction that takes the full quantity of G and transfers it to B in the absence of R, everything colored red. So only when the little r pops up. And then we have the full quantity of G that gets transferred to B only in the absence of R. And at this point in the cycle, everything is going to self-time. But this is where the user can come in and dump the quantity of X. And you'll see that he doesn't have to come in and dump the quantity of X at a precise time. But the quantity of X could be sitting here at the input colored B. Just bear with me until you see the full system, and hopefully it'll be clear. So now the other reactions that we'll throw in are the reactions that do the computation. So what's going on here? Well, I'm going to have 2A goes to the output Y, and 2C goes to R. So the input X will be split into types A and C. And then we're going to cut the quantity of A in half to produce Y out here. And we're going to cut the quantity of C in half to produce R, which is the input value that sits on the input to our delay element. So those are just the multiply by a half operations. And here, the two reactions that produce Y, we have one that produces it from 2A, and the other one that produces it from the output of our delay element. These just both produce Y. If you have two reactions that both produce Y, then you sum Y together. So you have Y that appears. And the system then proceeds like this. Okay. How about, let's stop here since it's time. But I'll post the slides, take a look at it, because it's, let me just show you the full set of reactions. Next slide. So this is the full set of reactions. Here we go. Full set of reactions to achieve the moving average filter is simply going to be a bunch of absence indicators that produce the lowercase types only in the absence of the capital color-coded types. And then the reactions that take X to A and C, R to G, G to B, B to Y. And the reactions that take 2 of A and 2 of C and produce Y of R. And this entire system now is self-timed in the sense that it'll produce the output quantity Y that will sit there, limiting what happens, because once you've got red sitting at the output, nothing that can process the input B is present. Only once you remove all the output Y does the next cycle begin, where it takes the input colored X, go through the RGB, and produce the value that sits there, waiting till you remove all the Y. And then once you remove all the Y, the amount of X that's in there gets taken in. So the system is self-timed at the output, meaning it's only when something consumes the full output quantity does the next input quantity get processed. And the only requirement in terms of when you dump your input in is you must dump your input in before you remove all of your output. So you can take your time. The system can sit there for 10 hours, and you can say, okay, I'm going to dump the next quantity of input X in. Now I'm going to consume all my output quantity of Y, and then it proceeds. And then you can take your time and dump in your input whenever you want, and then you take the output, the value gets processed. Okay. All right, so let me revisit that next time. Regarding the homework, the submissions, there was some question about whether you should submit your code if you're turning in a paper copy. And I guess very few of you are turning in paper copies. So I gave you guys till midnight. So if you're turning in paper copies, then yes, please email your code separately so we have an electronic form of it. Okay. Yes, please.
Can I talk? I just wanted to know for question number 2 for the value of epsilon, do we just have to take epsilon equals to
Yeah.